Greetings everyone, this is Non-Expert here back again with another video. Today we'll be solving problem number 36 and difficulty has been rated at as medium. This problem was asked by Dropbox and let's just get down to it. So given the root to a binary search tree, we need to find the second largest node in the tree. Cool. So actually there are a variety of problems which are similar to this. You will probably get, find the second smallest node or second largest node or the kth smallest node or kth largest node. But the approach for all of them is the same. So today, fortunately, we found a similar problem on LeetCode, and the problem is called as the kth smallest element in a BST. So as to find the kth smallest element in a BST, it's pretty simple. All you have to do is you just have to do an in-order traversal. And in-order traversal in BST is actually the most simplest thing ever. You do a recursive call and you keep on getting it from there. And just store all the values inside a list, and whenever the iteration is or the recursion is done, the list whatever you've formed, you can sort of use that in order to understand what's the kth smallest element. Or if you're sort of if you want to find the largest element, the kth largest element, the idea would be the same. What you would want to do is, instead of doing an in order, so I'll just write this down for smallest, what we do is we'll do an in order traversal, whereas for largest values, kth largest values, what you want to do is you want to do a reverse in order. And a reverse in order is sort of, it's the exact same thing that you would think about it. Instead of going from the left first, you do the right, then the middle, and then the left. So the way your iterations goes is right, val, and then left. And in order, it's just normal left, val, and right. So it's a pretty simple approach. There's not much there to it. But today, since we're going to create smallest element in a BST, we want to do it with the most optimal performance as well. And today, the way we're going to do this entire, try to solve this entire solution is by basically using a concept of in-order traversals, but using iteration. Again, most of you would not be familiar with this, but if you are, that's awesome. But the entire explanation is that in a recursive in order traversal, what you do is you try to push everything inside a stack, a recursive call stack, and you keep on popping out those values from there. And we'll be using a similar approach as well. So before we start, let's just start with our base conditions. Just say, hey, if root or k does not exist, we just return nothing. And now we start with our actual approach. So basically what we're going to do is we're going to create a list and call it a stack. And as you know, inside Python, you can use a normal list as a stack. It's pretty simple because whenever you do an append, the append sort of goes at the last value. So it's using the last in property. And whenever you do a pop without any parameters, what happens is it pops out the last value which you have. So in you just say that it's the first out. So last in, first out, that entire thing is sort of that property is handled. Um, cool. So what we're going to do is to do an in order iteration traversal, you need to do a while loop. And the first thing that we're going to do is we're going to go till we're going to traverse through all the values which are on the left and then move forward from there. So let's do that. We'll do while root exists. Basically keep on pushing in the root value or the node inside your stack. And as you're doing that, update the root as well. So make it point to the left value. So what's going to happen is that we're going to keep on getting iterated or keep on going till the left till it hits the none. So that's that. So as you can see in this example, as they've given over here, what's happening is you have 3, then 1 is going to get hit, and then basically that iteration needs to stop over there because 1 is the minimum. And the way you sort of go about it is that whenever you hit this particular condition that root is no longer present, basically you pop out a node from the stack itself. So you do node node stack pop. So you pop out the element which is there, and also since we want to find out the kth smallest element, we decrement k, and we say that hey, if k is equal to 0 or if k does not exist, basically just return node.val because we have hit that kth smallest element. And if that's not the case, basically we update our root to tell it to basically tell our node to point to the right. And that's basically it. There's nothing more over here. So as you can see over here in this example, what is going to happen is you're going to have 3 and 1 inside your stack. And then 1 is going to get popped out. So 1 is the first element, first or smallest element. Then what's going to happen is the thing which has been popped will, try to look at its right. So the right is going to be 2. So, we're going to come over here. So what's going to happen is node dots when you have node as 1, your root will become 2. So while root is 2, it will get appended inside your stack. So your stack will have 2. Then you'll pop that value out. So you will have 2 over here, and your second smallest element would be 2. Um, and then basically you would not have anything inside your root, so this condition would not run, but your stack would still be filled up with 3. And that's just the entire operation. So then you'll go to 3, and then you'll try to pop that thing out and try to use it, and if it's sort of working, then you do node.val. Otherwise you go to sorry, you go to the right. And that's basically it. So let's just try running this, and hopefully it should run. And while it's running, I would like to mention that this is the more optimal approach. And the reason why this is a more optimal approach is basically that you're terminating out your uh, iteration or whatever traversal as soon as you hit the gate smallest element. And after that, you don't want to do anything else. So basically, that sort of um, helps you out and sort of works out a complexity of h plus k, which basically h is the height of the tree, and then so on and so forth. And that's your worst case scenario. So all in all, it's a pretty optimal approach. And this is running, as you can see over here. Let's just try submitting it. And awesome, it is working, and you can see it's faster than 92% of the solutions. And the reason for that is because of the iteration approach. It's not the most memory efficient. Again, that's just because you're using stack. And that's basically it. Again, I would sort of urge you to check out the link given in the description below and try solving this on your own before you look at this video. And it's a pretty simple problem all in all. Again, if you did like this video, do give a like, and if you have any comments, you can leave it in the comments below. Also, try subscribing to this channel. We are discussion over here, and we would love to have you. And if you've already subscribed, you're awesome. We all know it. And have an awesome day. Thank you.